Okay, so lesson 3.7, as you can tell, is quadratic inequalities. And there's going to be two methods for solving quadratic inequalities. We're going to start with a graphing method, and then we're going to move over to what is known as an algebraic method. So that's going to be the focus of today's lesson. Let me start off by showing you the graph of this particular quadratic inequality. We're going to have to draw on what we've already learned as far as graphing quadratic equations. So in the beginning, you can treat this as though it wasn't an inequality. Just think of it as an equation like this, or equal to 0. Y would be the function form. Y equals that quadratic function. So what I'm going to allow you to do in this case, instead of finding the opposite of b over 2a, find the AOS, plug that number back in, let's find out first where this particular graph, if it crosses the x-axis, where does it cross? So in other words, we're going to solve this as though it were an equation equal to 0. And how do I solve a quadratic equation? Well, I've got choices. To me, factoring is the best choice, but this doesn't factor, so I'm left with quadratic formula, completing the square. I've got all of those at my disposal. So I'm going to use the quadratic formula to find out what the two solutions are, and if they're real numbers, that also represents where this graph is going to cross the x-axis. So let's just plug into the quadratic formula. Opposite of b plus minus square root of b squared minus 4 times 2, which is 8. 8 times negative 3 is negative 24. And all of this is going to go over 2 times 2, which is 4. And I'm down to this, and I hope you have your calculator handy, because we are going to approximate, since there is no perfect square root for 28, we're not going to get rational number answers. So let's find out what the two decimal results are. 2 plus root 28 divided by 4, somebody give me that, and then somebody give me 2 minus root 28, and that result divided by 4. So let me know when you get something. Carly, do you have 2 plus? Okay, that's fine. Negative 0.82, yeah. Okay. All right, that sounds good. And who has the other one? 1.82, is that right? Okay, so I'm going to approximate this graph, this parabola, obviously is going to cross at these two areas, so that's really, really close to negative 1. And it's really close to positive 2. Now before I go to, we're good so far. We'll just keep on going from here. Based on the fact that this lead coefficient is positive, would I conclude that the vertex would be down here or up here? Okay, it's going to open up, so the vertex has to be down here. And it's got to be halfway between these two x-intercepts. So at this point, you have a choice. You could do the opposite of b over 2a. Remember, that's how we find the line representing the AOS. The AOS should split right down between those 2 points. So what is the opposite of b over 2a, looking at our original equation? Opposite of b over 2a is 1/2. Everybody get that? Okay, so let's just go ahead and use that. This is a little bit of review for tomorrow. How do I get the rest of the vertex? The AOS also means that's the x-coordinate of the vertex. So how do I get the y? Just plug it in, okay? So let x be 1/2, both of the x's obviously, and see what comes out if you input 1/2. What do you got? 3.5 negative, okay? All right, and this is really all we need, these 3 points. In the past we've used 5 points, but really we're just going to utilize the two x-intercepts and the vertex. So I'm going to approximate 1/2 negative 3.5. Okay, now I'm ready to sketch the parabola, but I'm going to rely now on the inequality. And I notice that it just says greater than. It does not say or equal to. So think back when we've done linear inequalities, that meant that we did a dotted line. Well, in this case, we're going to do a dotted or a dashed parabola. Okay, and now I also look at the inequality to determine shading. And we've looked at similar examples in the past. I used the expression greater than is above the line. We've done some absolute value inequalities in the past, and this is very similar. Above the line is how we represent greater than, and I know these aren't really lines, but you can think of them as lines. The greater than area would be above, actually both of these parts, these two curves that make the parabola. So to finish this off, to show the greater than, all of the points greater than would be the shaded area inside the parabola. So you can always think greater than is above the line, less than is below the line. And I know you're thinking, well, those aren't lines, and that's true, but it's the same concept that we used when we were doing absolute value. So notice, when it's a function where y is greater than or y is less than, it really doesn't matter, you've got y and x, our solutions are all of the x, y coordinates that make this true. Okay, so that's pretty important. If you see y and x as part of your inequality, then you're going to be shading, if there is a solution, it's going to be an unlimited number of x, y coordinates that either fall inside or outside the parabola. Okay, questions on that first example? All right, let's move to solving. Notice how the problem has changed. The inequality doesn't say y is greater than, it says 0 is greater than. Okay, when I solve this inequality, now I'm looking for numbers for x that make this true. Okay, and I'll show you what I mean by that. Okay, so first thing I'm going to do is, just because this is a preference for me, I'm kind of a linear thinker, I guess, so I'm just going to turn this around. I prefer to see this in this form. And it says 0 is greater than that, so I'm just going to make it that is less than 0. And in a similar way, I want to think of this as an equation. And let's solve the equation so that we can know, since we've got to solve by graphing, let's see if this graph crosses the x-axis. And if so, solving it will tell us where. So once again, if you haven't already, you can jump into the quadratic formula since this doesn't factor. And let's see what comes out. Opposite of b plus minus square root of b squared minus 4 times a times c all over 2 times negative 1, negative 2. Simplifying underneath the radical, we got 49 plus 48. I believe that's 137. Is that right? What is that? 49 plus 48. 97. Way off. And once again, since we're going to approximate x-intercepts, we need to get a decimal. You can round it to 2 decimal places. Give me the approximate value of the square root of 97. Do all the math, just like we did on the previous example. And give me what those two numbers are. So when you get one, just raise your hand, let me know. Johnny? Negative 1 point, what's that? Negative 1.442. Okay, and does somebody have another one? Yeah. 8.42. All right, so these solutions represent x-intercepts. So it's about negative 1.5. And this is about 8.5. Now I made dots here, but I'm going to, before I go any further, I noticed that the inequality says just greater than. And remember, when you're solving this absolute value inequality where it's really set to 0, we're looking for values of x, only x values that make this true. So before I go any further, since it doesn't say or equal to, these actual x-intercepts are not going to be part of the solution. So I'm going to change these into open circles. If it had said greater than or equal to, they would be solid. Okay, and now we're going to go through and just build the parabola. So let's find the vertex. You looked at an example of that already. You can do the opposite of b over 2a to find the AOS. So go ahead and do that. And when you found that AOS number, just turn right around and plug it in for x. And you'll find the rest of the vertex. So who has the x coordinate of the vertex? You've got the opposite of b over 2a. 7 halves, 3.5. Okay. And go ahead and plug that number in. And let's get the y. Okay, 24 and just a little bit more. So I don't have that many spaces, obviously. So the goal of this problem really isn't to build an exact parabola, even though I want you to be as exact as you can. The real goal is to find all of the, I'm going to put a dot up here to represent the vertex. The goal is to find the x values that make this inequality true. And we're going to use the parabola to help us determine what those values are. Okay, so what this means is, I'm going to go with my version here. I just turned the problem around, and here's what this says. What part of this parabola, what part of the graph of this function falls below the x-axis in terms of x coordinates? Okay, so let me say that one more time. This reads, if I'm reading it in words, let's describe in terms of x coordinates where this parabola lies below the x-axis. Well, I'm going to shade in the part of the x-axis where the parabola is below. It would be going to the left of this open circle, because that's where the parabola is below, and it will continue to go left as it goes down. And that's also happening going to the right of this open circle. These two red shadings represent the x coordinates where this parabola falls below the x-axis. That's what this less than 0 means. Yes?
Does it matter if the lines are dotted?
Well, in this case, they won't be. The only thing that will be open or closed, since when you've got 0 involved, it will be either these are open or closed, the actual x-intercepts. That's a good question. Okay, you with me so far? Now we're going to state the answer in inequality form. Okay, so part of my answer is all of the numbers that are less than this x-intercept, which we called negative 1.42. So I've got all of the x's that are less than negative 1.42. That's part of my solution. And then I've got all of these x's that are greater than this x-intercept, which was 8.42. And that's our answer. Okay, any questions on solving by graphing? Let me go ahead and complete this vertex 24.25. Okay, let's try another one. And I've given you problems here that match up. These examples match up to these homework problems. So let's just jump right in and see if this parabola is going to cross the x-axis. Let's find out where. So what that means is treat it like an equation temporarily and solve it. So I'll give you a second to use the quadratic formula. And the solutions also, again, I know I'm repeating myself, but it's important. The solutions to a quadratic equation are also the x-intercepts for the graph. Okay, so we've used the quadratic formula, and we got our two solutions for x. And Gage, give me one of those. I got positive 2.09. Okay, and so what's the other one, Gage? Good, negative 0.84. All right, so let's just approximate those on our... Now this time, since the original inequality says or equal to, they're going to be solid circles. They're actually going to be part of the solution. So just barely to the right of 2 and almost to negative 1. All right, and we really just need the vertex as one other point to complete the graph. So opposite of b over 2a works. Let's see, Matthew, can you give us that opposite of b over 2a number? 5/8. Does that look good to everybody? Okay. Now you got to turn around and plug that in to finish off the y coordinate of the vertex. Anybody have that for us? Katie? 8.6. All right, so we'll approximate that's just about a half. 2, 4, 6, 8, and just about 8.5. And let's just go ahead and draw our parabola using those 3 points. Okay, now we're going to look at the original inequality, and notice that it says greater than equal to 0. So putting this in words, it would say what part of this graph, of this quadratic, lies above the x-axis. And the part of the parabola that's above is all of the numbers in between. And again, we're just looking for x coordinates here. Those are our solutions. And if I shaded the x-axis to represent the x coordinates that would be above the x-axis, I would shade just this area right here. And putting that in inequality form, I'm going to do a between statement. It's all of the x's between negative 0.84 and 2.09. And I'm going to say or equal to because that's what the original inequality said. Okay, So far, so good? Any questions? All right. I think I'm going to skip this one if that's all right. I think you get it. It's just more of the same. Unless you have a question, let's jump to solving algebraically. These are a little bit better. Don't have to graph at all. You do want to approach it the same way as far as finding the solutions. Pretend for just a second that this is an equation. And we'll start off with a nice one because this equation actually can be factored. Don't have to use quadratic formula. There are factors of negative 16 that add up to positive 6. Positive 8. Negative 2. So our two solutions come from these factors. One of my solutions will be negative 8. The other solution will be positive 2. So here's what solving algebraically entails. We're going to make a number line. And on this number line, I'm going to place these two numbers as they would appear. Negative 8 would be obviously to the left of positive 2. So solving algebraically looks like this. I'm just going to use dotted lines to break this number line up into 3 sections. You are going to choose a number, one number out of each of these 3 sections to test. And you're going to test the original blue inequality to see if that number makes this a true statement or not. So for example, I'm just going to choose negative 9. I'm going to plug negative 9 in for both of these x's, simplify, and when I plug negative 9 in for the x's, is it less than 0? Try it out. So negative 9 squared plus 6 times negative 9 minus 16, is that less than 0? No? So what we've proven is nothing to the left of negative 8 works. I'm just going to draw an X there. My solution cannot come from the set of numbers that are less than negative 8. Okay, so now let's pick a number in between, and the easiest choice is 0. Let's let x become 0 here, and you get negative 16 is less than 0. True or false? True. So what we've proven now is all of the numbers between negative 8 and 2 will work. And so let's pick another number to the right of 2. Let me just show our choice here. Blue will be our choices for tests. So the logical choice is 3. If you let x be 3, do you get a true statement? No, you do not. So the range of numbers between negative 8 and 2 represent the solution. And since it doesn't say or equal to, our answer looks like this. All of the x's between negative 8 and positive 2. So that's an example of the solving algebraically method. And we'll try one more, and then I'll let you get started on the assignment. The first thing you should always do is put this in standard form related to 0. So you could start like this. I'm just going to add 30 to both sides. Again, this is just a preference thing. You don't have to do this, but I like to turn these around so that the constant is always on the right side of the inequality. I haven't divided by negative yet, but that would be a good thought. Yeah. Okay. Another great one because it factors. There are factors of 30 that add up to 11. So for now, I'm going to treat this as an equation to find out what the solutions are. And those solutions represent the places on my number line where I have sections that I'm going to test around. Okay, we found the solutions. Just make a little number line. Doesn't have to be anything fancy. I'll put negative 6 to the left of negative 5. This time, you don't have to do solid lines. I'm just using these dotted lines to show the separation between the three groups. But when we write our answer, we need to remember to use or equal to as part of the solution. So do your test. I'll give you a minute just to pick three numbers, one number out of each section. Plug back into the original. I would probably use this. Take each of your numbers one at a time, replace x, and see if you get a true statement. And we'll come back together in just a... Okay, hopefully you've done your test and you've discovered that the numbers less than -6 work. How many of you figured that out? Good. The numbers in between do not. And the numbers greater than -5 work. And so we actually have a union of two different sets of numbers that represent our answer. So all of the numbers less than or equal to -6 are part of the solution. Or we could also have all of the numbers greater than or equal to -5. So I gave you one example of a between statement where all the answers in between two numbers. And this goes back, if you remember, back to compound inequalities. This would be considered like an or statement. Or the fancy mathematical term would be union. The union of those two sets. All right, what do you think? Not bad? Really? What number did you use? Okay, so let's check that out. -7 squared plus 11 times -7 plus 30